Okay. Hello, everyone. Thanks for coming. So I'm going to talk about efficiently serving large language models at scale, something that we're working on at IBM and folks in lots of other places too. So just give a quick introduction to myself. I have a cloud background. I sort of work on distributed systems, and in particular, infrastructure for machine learning systems. I was involved in productizing the original Jeopardy IBM Watson, if anyone remembers that, and then scaling a lot of IBM's cloud machine learning products and services like Watson Assistant, Watson Discovery, those kinds of things. I've been more focused on the inferencing side of things, and in particular, I designed a framework called Model Mesh, which was open sourced. And that's for serving very large numbers of models and efficiently managing, if every user has their own model and you've got lots of small ones, scaling them out and effectively kind of managing a distributed cluster of them. And I contribute to some other open source projects. If any Scala people here, I sort of committed to the Netty project. Model Mesh used Netty a lot, but was built on Java. So yeah, about a year ago, or maybe a year and a half ago, I switched to look at serving large language models. That's obviously quite a big difference because instead of large numbers of small models, it's like a small number of large models. And it's very interesting space to be. There's lots of research coming out every day and opportunities to kind of look at how you can apply engineering to the latest research in the space. So in this talk, I'm going to sort of give a little bit of a journey of what we did to optimize like LLM inferencing when we first got involved. And as part of that, explain one of the sort of key techniques called continuous batching. And then I'm going to sort of, depending on time, I'll go through a bunch of other techniques that have emerged since then as well. So if you rewind to summer of 2022, this is before ChatGPT came out in November, December of that year. OpenAI had GPT-3, but it was not that many people knew about it. It was mostly a sort of research thing. But clearly, like a lot of people were seeing the potential, but it sort of came with restrictions in terms of what you could do with it commercially. So there was a large open source effort called Bloom that some of you may be familiar with. It was an open collaboration between lots of organizations, and they trained a 176 billion parameter model that was meant to be sort of the open source answer to GPT-3. So this had been trained, but because it was so large, no one, there was not much known about how best to deploy such a large model. The weights were like 350 gigabytes or so. And if you want to serve it in GPUs, there are no GPUs that large, so you have to kind of have a whole node full of 80 gigabyte A100s and spread all the weights across these. And in IBM, we wanted to give researchers access to this. Obviously, they can't all deploy their own because the GPUs cost so much and they're so scarce. So we were looking at, okay, how do we sort of deploy like a Bloom as a service? So initially, there was an implementation of Bloom in the Hugging Face Transformers library. This is what most people used then, at least, and still, for the most part, for sort of working with transformer models. But the size is a problem, so there's sort of these other frameworks that you can be used with it. One is called Accelerate, so that allows you to split up the layers of the model across multiple GPUs. The trouble with that is it's kind of slow because it does one layer at a time, so if you're trying to do real-time inferencing, it's not a great solution. The other way is if you split up the model by layer, so you split each layer across, each of the layers is split across each GPU, then you can run the layers in parallel, or you can run each layer in parallel, sorry. And there was this is called Tensor Parallel. There was an implementation of this from Microsoft called Deep Speed Inference. So this is something we started, and we sort of wrapped it at a web server and had a little queue in front, and users could sort of submit batches of requests to be inferenced by the LLM, and we pass this to the Hugging Face generate method in transformers. This first implementation wasn't not ideal, because once you have more than one user, things slow down quickly. It takes a long time to do this auto-regressive inferencing, which means it's being done token by token. And so, if you're generating a large amount of tokens, that's going to take a long time. And if another request comes in the meantime, it has to sort of basically queue up and wait till that's finished. So this would result in a low GPU utilization, low throughput. Most requests are kind of single input or like a low batch size. Instead, like what a lot of the servers do is a sort of dynamic batching, where you can kind of auto batch requests that come in, put them into a batch, and then like pass that through. The transformers library took batched input. This is okay if all the requests are kind of similar, but if they're different lengths, then it's kind of a problem, because the short ones are going to wait for the longer ones. The amount of time it takes to run a request is basically proportional to how many tokens the request generates. And also the parameters, like if any of you guys have used ChatGPT, or well, actually not ChatGPT, but some of the other hosted LLMs, there's parameters like the temperature and top K and top P and things like that. And if the requests have different parameters, they can't be combined into the same batch using the generate method. So solution to this was to split open the generate method, and inside there's basically a loop where you're generating each token one at a time, and instead of applying the parameters to choose the next token in the same way across all of the entries in the batch, we sort of keep track of the different parameters, and we can do those one by one for each of the elements in the batch. This is also nice because we can then stream the output. Now we have we're in the code that's actually doing this loop, and we can then also finish the shorter sequences as soon as they finish, rather than having to wait for the longer ones. So that was a big improvement. There's still some problems here, because if you have very different input and output lengths, then the batch is still going to wait for the longest one to finish before you can start a new batch. Some would finish a lot earlier than others, and then there's requests waiting in the queue. The idea is the sort of key idea is to modify the batch mid-sequence. As sequences in the batch finish, you can prune them out, and then add other sequences into the batch, which sounds kind of simple, but actually there's a little bit more to it than that. One of the key optimizations that's used for inferencing is called KV caching. Every time you generate a token, you basically calculate the attention the attention between that token and all the preceding ones in the sequence. So there's a lot of redundancy, and you can cache like everything up to the current token. You can cache all of those weights. So typically, you process all the tokens as a first pass. That's called a prefill, and then from then on in, you just send in the next set of tokens for each of the sequences in the batch, and you keep this cache of tensors that have all these weights. So the trouble is, if you're sort of processing one batch and then you want to add some more requests in, you need to kind of first process get the new batch into a similar state as the old one. So the way it works is you run the prefill step for the new batch, and then you can basically do some sort of tensor manipulation to concatenate the KV cache of the new batch with the existing batch to sort of form a new combined batch, and then kind of continue from there with the token by token decoding. This is kind of a visualization of that. So at the top, you've got a batch. The zeros are kind of represent padding tokens, because we pad the shorter sequences, and then the sort of orange column is the new tokens that have been chosen for each of the sequences in the batch. And then you see that one of the sequences completes. At that point, we can kind of prune it out of that first batch, and it means we have a bit more space now in memory, because the problem with the KV cache is that it takes up a lot of GPU memory. So that's typically the the main constraint for how large batches you can run, which in turn is the constraint for the amount of throughput. And so now we've reduced the memory that the KV cache takes. We can pre-fill a new batch and then join the tensors to create the KV cache, which is at the bottom there, and then continue. So what you have in effect is kind of a never-ending batch where, you know, as new requests come in, you sort of add them in if there's space, and then as they complete, you prune them out, and then they just sort of all interleave. So you never really finish. It's more like a train than a batch. Yeah, a lot of the optimizations are sort of centered around how to best deal with the KV cache in a way, because manipulating the cache because it's a large amount of data in the GPU. That's one of the main overheads. So going back to our sort of Bloom as a service, we were sort of looking around at the time for how we could improve this, and Hugging Face came out with a blog of how they had done this. They sort of made their own tensor parallel implementation, and they had they'd done a lot of the things that I'd mentioned in terms of splitting open the generate method. They hadn't, so that, you know, requests that are finished could finish early, and also they could, you know, have heterogeneous requests with different decoding parameters. So we rebased our code on this, and then started to look at, okay, how can we do this technique of like adding new sequences into the batch that I described. Around that time, a new project sort of appeared also from Hugging Face called Text Generation Inference. This was like a redesigned sort of production grade server based on the same thing, and it had a front written in Rust, which was decoupled from the back end sort of Python shard processes that actually do the tensor manipulation and run the model. The front end sort of dealt with the batching and the request queuing and that kind of thing. They'd also incorporated this sort of never-ending batching logic. So we quickly adopted this. We actually forked it ourselves and, you know, started to make some of our own improvements on there. So we sort of now work from something that was originated from this project, but we also sort of worked with them originally and contributed a number of things back. So the term, you know, that was adopted for this, I think I was the the first person to kind of think of that name, but it got picked up and it's used now in a lot of the other projects that are doing a similar thing. Is continuous batching. There was, I think the earliest reference is actually in a paper, they didn't use the same name, but of a technique that was similar to this, called iteration level scheduling. It was a paper called Orca. It's like not an open source project, but it's a paper that was like came out a few months before that. So the next thing we looked at was how do you decide when to add new sequences into the cache. So you have a queue of these new requests come in, of sequences of different lengths, and they all have different max number of tokens that they're going to be generating. How do you figure out how many of these you can add? And typically when the servers do dynamic batching, you just set a maximum batch size and you just sort of fill up the number of sequences until you get to that size, and as more are removed, you can add more in. The trouble with that is that the memory that is the limiting factor is a function of the sequence length as well as the batch size, the number of things in the batch. So, you know, if you were restricting the batch size, you'd have to figure out, like, okay, what's the longest sequence length I want to support, and then you need to size your batch quite small to accommodate that. So one of the things we did next was to introduce dynamic batch sizing, which decides whether or not to add sequences into the batch based on how many input tokens they have and how many output tokens, and you know, they're predicted to produce. And so we can figure out, okay, if we add this, would we exceed the size of the KV cache as the sequence is generated? And if not, then we can add it in. Otherwise, it sort of stays in the queue. So the nice thing about this is we can support much longer sequence lengths, and the batch size will just sort of flex to accommodate that. If the sequence lengths are very large, then we'll end up with small batches. But if they're sort of a medium size or a small size, then the batch will kind of flex up, and we can we can have much greater throughput with much larger batch sizes, up to say 128 or something, or even 256. Okay, one of the next optimizations was, and this was one we that came from the upstream sort of Hugging Face project when we incorporated it. But flash attention is a technique that really optimizes how the matrix multiplications are done in a transformer, how the attention's applied, and sort of making use of the layered GPU memory caches. And there was a good implementation of that, I mean a sort of reference implementation, which allows you to provide the cache in a kind of contiguous format. So instead of having a batch dimension, you can sort of concatenate all the sequences and provide offsets. And so as well as the actual the operation to compute the attention being faster, this meant that you can obviously pack a lot more tokens in, especially when the sequences are variable lengths. Before, we'd have to sort of pad to create these rectangular batches. And that's, this is just showing 2 dimensions, but when it's the KV cache, you have additional dimensions, which, every one of these numbers, these tokens, is actually a big chunk of memory. So you have all these wasted zeros, the padding tokens. Once you switch to the sort of the variable length sequence single batch dimension, then we can just save a lot of memory by packing a lot more in, and then, the algorithm to fill up the batch is similar, but it just means we can get a lot more in. That helps a lot with throughput. Another optimization is vectorizing the decoding. So one of the problems when we split the generate method and don't apply the same decoding logic to each of the rows in the batch, this is where you're selecting from a probability distribution over the possible next tokens. The way you do that might be different for each row in the batch now. And so what we'd had to do is sort of a loop and process each one separately, and each of those involves some GPU operations, because all of these scores that come out for each of them are in tensors on the GPU. Once the batch size gets quite large, this becomes a bit of an overhead. So vectorized decoding is basically where you create tensors that sort of combine all of the parameters across the batch. So if they all use different values for top K, for example, you can put those all in a tensor and apply it to the column of the probabilities at once. So basically, vectorizing each of those operations. So that was a big speed up. So this is just a picture of our version of the server showing the Rust front end and the Python shards on the right-hand side. And basically, the batching loop on the Rust side is deciding on which things to batch, and like between every token, it goes back and forth and sort of controls how the tensors are put together, and the forward passes are done on the Python side. So something that came out very recently from Microsoft is a technique called dynamic split fuse. This is in their sort of revamped deep speed inference, or deep speed fast gen, I think they call it now. So this is actually a problem with the way that the continuous batching works, as I described it, is you have to kind of interrupt the flow of next tokens for the current batch to add a new batch in. And the prefill operation, where you're computing the initial weights for for all of the input tokens, is actually quite expensive computationally. So that takes much longer to generate that first token than all the subsequent tokens. And it's also bound by the compute rather than the memory. So the later steps are memory bound. The first is compute bound. So you don't have necessarily great, especially with smaller batch sizes, you don't have great utilization for just the next token stages. So the idea here was to sort of amortize the prefill step across multiple decode steps, like next token steps. So they sort of, if you have a new batch to add in, you can actually combine the prefill operations with the decode ones to just enough to saturate the compute and not slow things down. But it means that you're then able to soak up more of the utilization, and you have less of these kind of bubbles, as they describe it. So that's very interesting technique. for helping with that. Another one that was, it's been around a few months now is a new inference server called VLLM, and the big contribution they had was to apply sort of virtual memory principles to the KV cache. So one of the other problems with the KV cache is it's a tensor in the GPU that keeps growing, but because when you're generating these sequences, you don't know when they're going to stop. And so you don't know how much space you need to reserve for it. And if you don't reserve space, then you have to copy lots of data on every single token that's generated. So they basically implemented kernels which can work with non-contiguous tensors. So instead of having to sort of copy the whole tensor each time, you can basically divide it into blocks and just reference chains of blocks without having to do the copying. And then the kernels can work on those directly. And it allows for additional things like sharing, reference counting and sharing, but the same data between sequences if you've got duplication, and that allows for further efficiency in how the KV cache is put together. Another sort of technique is an observation that a lot of the times the next tokens that you are predicting are actually quite easy. There's very much more obvious potential next tokens to other cases, like if you're generating code or something like that. And so what you can do is use a small model to kind of predict a bunch of tokens into the future, and then use a larger, more accurate model to sort of verify those. The nice thing is you can actually, because you process all the tokens in one go, you can verify a batch of tokens. Usually, instead of having to wait for the next token, you can do the next 4 tokens, for example, together and see whether they would have been chosen by the large model. And if not, then you can if say in this example, the were chosen by the large model, but the car isn't the right one, or the bus isn't the right one, and you get car instead, then you can just take as many as you get and then revert to doing the predictions from there with the smaller model. So this allows you to kind of jump ahead much more quickly than having to do these steps that depend on the prior ones. So since we got involved maybe 18 months ago, there's been an explosion of activity in this space. I mentioned VLLM, that's one of the most prominent servers now, and they sort of incorporate a lot of the things, the techniques like continuous batching, and they're looking at incorporating all the new models and the new techniques that come out. There's a bunch of others here, like I mentioned the deep speed fast gen. NVIDIA came out not too many weeks ago with something called TensorRT LLM, which is their sort of version of this. There's a project called FlexFlow from Stanford. They were sort of focused on the speculative decoding stuff, but now incorporating a lot of these other techniques. So what we sort of find is there's announcements every now and then of one of these new projects that say, okay, we have this new technique, and we're much faster than the others, and they do a bunch of graphs, and then the other projects will incorporate that technique and then maybe do something different. And so there's all this sort of leapfrogging and everyone trying to sort of do more efficient variations of the existing techniques and come up with new ones. So it's kind of a very interesting space, and it's continuing to change. Some other techniques that I didn't cover are sort of compiling the graphs using something like torch compile, so that you don't have to do it in Python, like things that would take multiple GPU operations. If it was running in Python code, you can fuse into single operations. CUDA graphs is similar to that. Quantization is where you shrink the size of the precision of the model weights, and that means you can fit much more onto the GPUs and so get more throughput that way. And there's a whole bunch of sort of sub-techniques of a lot of these that I could go into. I'd recommend, if you're interested, looking through some of these things and getting involved, because if you're a sort of engineer like me, and it's a very interesting space to sort of apply things. And then just final slide, to recommend this blog post came out a couple of weeks ago from the Mosaic ML folks, which is a really good summary of some of the things I talked about and sort of best practices for doing this kind of engineering. So thank you.